Today, we are going to learn about checking data quality with Xtriage. Xtriage will tell us if our data are going to be useful and if they have any unusual characteristics. In particular, Xtriage will tell us how accurate the data are. If we supply unmerged anomalous data, Xtriage will tell us in detail whether there is an anomalous signal. It will also tell us about ice rings, whether translational non-crystallographic symmetry translational NCS is present, and whether twinning is present. Twinning tests depend on whether translational NCS is present. If translational NCS is not present, we use the Wilson ratio, the ratio of the mean square intensity to the mean intensity squared, to check for twinning. If a crystal is untwinned, the Wilson ratio for acentric reflections is 2, and if the crystal is perfectly twinned, the Wilson ratio is 1.5. If translational NCS is present, a separate test called the L test, which is corrected for effects of translational NCS, is used. Xtriage can also help you check if your data are indexed correctly. Note that twinning can introduce false symmetry into the intensities. Xtriage can also check whether the systematic absences in your data match the space group you specified. Let's use demo data from the Phenix tutorials. In the main Phenix GUI, click on New Project, then Set Up Tutorial Data, and choose the Xtriage Analysis of SAD Data tutorial under Other. Select a suitable location to put this folder and click OK. In the main Phenix GUI, under the Data Analysis tab, select Xtriage. Let's put in a title. We can select our unmerged reflection data by clicking on Browse, selecting the SCA file, and clicking OK. For unmerged data in SCA format, the unit cell dimensions are not part of the data file. We can input them as 114, 114, 32.5, 90, 90, 90. Check the space group as well. In this case, it is I4, not I4 sub 1. Let's run Xtriage now by clicking on the Run button. Xtriage will display a traffic light summary. Green is OK, yellow is worth checking, and red indicates a problem. The traffic lights cover common situations, from the resolution of the data, to intensity statistics and translational NCS, to completeness of the data. There is a pull-down menu where you can find specific information such as twinning statistics, information about your input data, twin laws, and possible symmetries of your crystal. Click on Resolution of the Data. This shows us our data goes to 1.75 angstroms with 145,000 reflections and a redundancy of 6.7. Note the mean I over sigma of 13, which is very high. Clicking Show Graphs and selecting Redundancy shows the redundancy ranging from 7 at low resolution to 6 at high resolution. Completeness is very high at all but the highest resolution. I over sigma goes from 20 to 3, fine for a SAD dataset. A CC1/2 plot is over a very good 0.97 at all resolutions. The half dataset anomalous correlation is over a very good value of 0.5 at most resolutions. Now let's examine twinning. The green light indicates no translational NCS. We can click and see that the largest Patterson peak has a height of only 6.9% of the origin. 20% would mean that there is translational NCS. As there is no translational NCS, we can look at the Wilson statistics. For acentric reflections, the Wilson ratio is 1.99, very close to the expectation of 2 for untwinned data. A perfectly twinned crystal would have a value of 1.5. We can also look at a cumulative distribution plot of intensities. The observed distribution for acentric reflections in blue is similar to the expected distribution for untwinned crystals. We can find possible twin laws in the pull-down menu. For this space group and cell dimensions, there is one merohedral M twin relationship with a twin law of -k minus h minus L. If there were twinning, you would use this twin law in refinement. Now let's look at our anomalous data. The traffic light says the probability of finding 5 sites with this data is about 94%. After clicking, this plot shows in blue the I over sigma we saw before as a function of resolution. And in brown it shows the estimated anomalous signal, which is 10 for an okay SAD dataset and 30 for a great one. The more data that is included, the higher the anomalous signal, up to a resolution of about 2 angstroms. This gives us an idea that 2 angstrom data is a good range to use in finding the substructure in this case. This next plot shows in brown the probability that we can find the substructure if there are 5 anomalously scattering atoms in the asymmetric unit. This probability comes from the anomalous signal in the previous plot. The chance of solving this structure is very high. We can look at a detailed table of the quality of this anomalous dataset as well. As a function of resolution, we can see the half dataset anomalous correlation, the estimated true anomalous correlation, the anomalous signal and its uncertainty, the probability of solving the substructure, and the expected figure of merit of phasing after solving the structure. Keep in mind that the purpose of Xtriage is to find possible problems and to see how useful your data are. If you find problems, then you will want to go back to data processing, fix the problems, and then run Xtriage again. Good luck! If you have questions or feedback, you are welcome to contact us at help@phenixonline.org or tutorials@phenixonline.org.